Delaware Tech, Chemistry 100, Chemistry 110, Organic Molecules and How to Draw Them. Well, let's talk about what an organic molecule is. Well, organic chemistry is the chemistry of carbon compounds. So an organic molecule must have carbon. That is the one constraint that it has to be called an organic molecule. Now, there are varieties of sub-definitions of organic molecules. Some people say that it's not organic until it has at least one carbon-to-carbon bond in it. But there are some molecules that only have a single carbon that are considered organic, like methane, and there are other compounds that have only one carbon, like carbon dioxide, CO2, that are not considered organic molecules. But we're going to call all carbon molecules, with just a couple exceptions like CO2, organic molecules. Now, that said, while organic molecules absolutely must have carbon in them, they can have pretty much everything else in them as well. You'll find carbon compounds that have hydrogens. In fact, most carbon compounds have hydrogens. But you'll also find carbon compounds that have oxygen, nitrogen, sulfur, phosphorus, all of the halogens, fluorine, chlorine, bromine, iodine, at least the common halogens, as well as technically everything else. As long as it has carbons in it, that's an organic molecule and therefore part of organic chemistry. So what are organic molecules? Well, there are a lot that you're exposed to every single day. Gasoline, petroleum oil, and kerosene, these are all organic molecules. In fact, these are a type of organic molecule called hydrocarbon. Hydrocarbon because it's only composed of hydrogen and carbon. So if it's only composed of hydrogen and carbon, that's a hydrocarbon. And hydrocarbons tend to be fairly non-reactive, but they tend to be able to burn very well. So you want to keep sparks away from them for obvious reasons. Many plastics are also organic molecules. In fact, most plastics are organic molecules, like polyethylene, polypropylene, polystyrene. Those first three are also hydrocarbons. They're only composed of carbon and hydrogen. Teflon, however, instead of using hydrogens, use fluorine, so it's composed entirely of carbons and fluorines, and it tends to be extremely stable to a variety of chemical reactions, and this is why we coat a lot of equipment with it to keep it from reacting to the environment. Almost every medication that you can take, with a couple minor exceptions, are organic molecules. They're carbon-based. The same thing goes for pretty much anything with a smell or taste, like perfumes, fragrances, and food flavors. These all are organic molecules. All of your food, with just the exception of water pretty much, are organic molecules. Sugars and more complex carbohydrates, these are organic molecules. Lipids and other fat-related molecules, those are organic. Proteins and peptides, as well as nucleic acids like DNA and RNA. These are all carbon-based. They have other elements in them like oxygen, nitrogen, sulfur, and phosphorus, but they are carbon-based compounds and therefore considered organic molecules. So let's look at a comparison between ionic compounds and organic compounds. And remember, organic compounds, most organic compounds are covalent compounds. These are the covalent or molecular compounds. So this is very similar to a table you've already seen comparing ionic versus covalent/molecular compounds, but we're going to specifically hone in on organic. So what types of elements are in them? Well, typically non-carbon-based elements are found in ionic compounds, but you have to find carbon in organic molecules, but it can contain just about anything else, as I already said. Types of bonds. Ionic compounds are held together with ionic bond interactions. You have positive charges and negative charges, whereas organic molecules tend to be covalent compounds made with covalent bonds linking the atoms. They can also form what we call isomers. We'll talk about that later, but isomers are molecules with the same formula but different structure. The smallest piece, as we mentioned before, for ionic compounds, the smallest piece of an ionic compound, since they don't come in individual molecules, we call it a formula unit. They don't actually exist by themselves. It's just the simplest ratio of the two ions that make up that organic compound. Whereas organic compounds, like other covalent compounds, are made of individual molecules. Because ionic compounds are made of positive and negatively charged ions, they tend to be very polar. They have obvious differences in charges, and this will also make them very soluble in water most of the time. Whereas organic compounds, since there's a large hydrogen and carbon content in most organic molecules, they tend to be nonpolar because carbon to carbon and carbon to hydrogen bonds are very nonpolar bonds, and therefore the molecules tend to be nonpolar. There are some exceptions. The smaller molecules that have a few other atoms in them that aren't carbon and hydrogen, we call those heteroatoms, like oxygen, nitrogen, phosphorus, sulfur, as well as fluorine, chlorine, bromine, and iodine. These things add electronegativity, high electronegativity atoms to the molecules, and those cases, the organic molecules might be more polar and more soluble in water, but most organic molecules are not very polar in water. Excuse me, not very soluble. Ionic compounds, as we mentioned before, because they're in these big lattices of ions, they're very hard to break apart, and therefore they have a very high melting point and an even higher boiling point. Whereas organic compounds tend to be covalent molecules, individual molecules, and those molecules are only held together with intermolecular forces, which tend to be much weaker than ionic bonds or even covalent bonds. And therefore, you will find that their melting point is much lower, typically under 300 degrees centigrade, and their boiling point as well is much lower. And as a result, you find that organic molecules might be solids, but they're frequently liquids or even gases, whereas ionic compounds are pretty much always solid compounds at room temperature. Since organic molecules typically have high carbon and hydrogen content, they tend to be very flammable, like the ones that I mentioned on the previous slide. So the simplest type of hydrocarbons are molecules called alkanes. Alkanes are made of only hydrogen and carbon, like a hydrocarbon, but what sets them apart from other hydrocarbons is they contain no double bonds, no triple bonds. So every carbon that's linked to another carbon is through a single bond. And we have simple alkanes, the straight chain alkanes. These are where carbons are linked together one after the other in a long linear chain. In other words, there are no branches in these particular ones, though there are branched alkanes also. We're only going to talk about the straight chain one first. If it's made with only one carbon, that would be methane, and we use the prefix methane, so that's carbon with 4 hydrogens. Remember, carbons form 4 bonds, so each carbon is going to be attached to either 4 atoms in single bonds or some combination of double, triple, and single bonds that add up to a total of 4 bonds. So since we're talking about straight chain alkanes, all the bonds are single bonds, and the carbons are linked together in long chains. Well, methane only has 1 carbon, and this is the predominant component of natural gas. If you have a gas stove, this is what you're burning. If you're in the laboratory and you're using the burner, this is the gas that you're burning on the burner. CH4, methane. Ethane has 2 carbons. It's a carbon linked to a carbon, and each carbon has an additional 3 hydrogens on it, so they each have 4 bonds. Propane has 3 carbons. So it's 3 carbons linked together, and each carbon has enough hydrogens on it to add up to a total of 4 bonds. So you'll notice at this point we have CH3 at one end, a CH3 at the other end, and there's a CH2 in the middle. So what these mean is in each group, the hydrogens are linked to the carbon that they're written next to. And as you add more carbons, you add more CH2s in the center to make this a longer and longer molecule. The 4-carbon straight chain alkane is called butane. And you probably heard of all of these names, but you may not have known what their definitions are and certainly not what their formulas are. The names after 4 carbons are from the prefixes you've already learned in nomenclature: penta, hexa, hepta, octa, nona, and deca. And by adding ane to the end, ane means an alkane. So if you see ane at the end, there are no double bonds, no triple bonds in this molecule, so it's going to be fairly straightforward. So pentane has 5 carbons, and what we call normal pentane would be straight chain 5 carbons in a row linked together in a long chain. Hexane is 6, heptane is 7, octane that you put in your gas tank is 8 carbons in a long chain, nonane 9, and decane 10 carbons. So let's look at different ways to draw organic molecules. There are actually many ways to draw organic molecules, and let's talk about a few of these. The first way is the most common for people that are first starting out looking at organic molecules, and this is called the structural formula or the structural format or the expanded structure. And what sets these apart is these structures show every single atom and every single bond between every single atom. And you can imagine they can get very tedious to draw, especially with large, complicated molecules. So you'll notice that we have 4 molecules here. Each one has a different form or a different number of carbons. The first one is methane, and I'll just write the name here for you. Methane. Let me get that up. There we go. That's methane. The second one is ethane with 2 carbons. Oops, excuse me. 2 carbons. Sorry, that shouldn't be there. The third one is propane with 3 carbons. And I'm sure you've heard of methane and propane, but you may not have known the structures here. The last one, you'll notice there's a 1 carbon group sticking out of the second carbon of the 3 carbon group. So this one, because this is a 1 carbon group and not a whole 1 carbon molecule like methane, we call this a methyl group. And you'll notice the main chain of this is a 3 carbon chain, so that's our propane. It's just missing the 1 hydrogen where we're attaching the methyl group. And this actually would be called 2-methyl propane, because if you count the carbons, there's the first one, the second one, the second one, and the third carbon in this propane chain. So if we continue on, let's look at some of the other ways to draw these. There's what's called the condensed structure, and there are actually multiple ways to do condensed structure. The first way I'm going to show you, you group each carbon with whatever is attached to that carbon, and then you show the linkages between the carbons with bonds. So methane only has 1 carbon, so you just write CH4. All 4 hydrogens are attached to that carbon, so you'd write it that way. Ethane, however, has 2 carbons, and each of the 2 have 3 hydrogens on them, so you'd write it as CH3 linked to another CH3. Keep in mind, this does not mean the hydrogens of the first carbon are linked to the carbon in the second carbon. They are not linked at all. The linkage is between the 2 hydrogens, as shown in this form. Between the 2 carbons, as shown in that form. And the hydrogens are there just to fill up the other bonds necessary to have a total of 4 for each carbon. So if you continue on, here's propane, and here's that methyl propane that I mentioned already. So you'll notice we just show a link between the carbons, and that's one way to draw a condensed structure. We have more condensed versions of the condensed structure. These are very common when people are typing out structures and they can't write these vertical bonds. They'll write it without the bonds, and then when they get to an item where there's a branch in it, they'll show it by putting parentheses. And this parentheses, the parentheses means whichever carbon that's following, that's the one it was actually attached to, as you can see with this bond right here. Now, the next method of drawing is not a standard method of drawing organic molecules, but it is a way of thinking about organic molecules that will help with the last way of drawing them. This is just the carbon chains, just the carbons attached to the carbons, and it's a pure carbon skeleton. It's not very useful for organic chemists, but it's very useful in learning how organic chemists draw molecules with the last format called the skeletal format. So you can think of these molecules as these groups of carbons that are linked together, and in your mind you just have to remember that each carbon has a total of 4 bonds, so you load up each carbon with whatever number of hydrogens it needs to total 4 bonds. In this propane here, we'd have 3 here, we'd have 2 in the middle one, and we'd have 3 on the end. And here we have 3 on the end, 3 on the end, and this one you already know has 4 hydrogens. Now we don't draw these lines, and in fact we don't draw these at all when we're doing the skeleton format, which is the last format based on this concept of a carbon skeleton. So in a carbon skeleton, we only draw the bonds if we're only talking about carbon and hydrogen. We don't show the hydrogens. There are some cases where we do write hydrogens. If hydrogens are attached to other types of atoms besides carbons, then in that case we would write the hydrogens out as well as those other atoms. Atoms that are not hydrogen or carbon, as I mentioned, are called heteroatoms. So we always write heteroatoms and the hydrogens attached to them. So in these carbon skeletons, and we would never do this for ethane, it's too small to bother. Propane would be the smallest we would ever do, but you have to remember that each one has 3 hydrogens here, 2 here, 3 here. We don't draw those, but you keep that in mind because each carbon has to have a total of 4 bonds. So you'll notice this middle one only has enough room for 1 more hydrogen. The other 3 are attached to carbons. So try to get used to drawing them like this. We're going to practice it a little more and go over the rules in another slide. So here are some cyclic alkanes. Again, these are made of only carbon and hydrogen, no double bonds, but they form rings. And the names for these are very easy. If you remember the propane, butane, pentane, hexane, heptane, octane, etc., you just put the prefix cyclo in the front of it to tell you it's a ring. So 3-carbon ring is cyclopropane, a 4-carbon ring, cyclobutane, and cyclobutane, while we draw it like this, if we looked at the actual molecule from the side, it's kind of this bent shape here, almost like a bent kite shape. If we look at pentane in a ring, that would be cyclopentane, and in fact cyclopentane will look like that if you look from above, but if you look at the side, there's a little bend in it. You're not responsible for these actual shapes. Typically these would be drawn in the standard geometric fashion, and that's good enough for now. And then cyclohexane is a 6-carbon ring. There are no double bonds in cyclohexane, so it's just a carbon linked to carbon in each one. And every one of these carbons in these rings, you'll notice, has 2 hydrogens on it. They all have just 2 hydrogens on it. So that's easy because each carbon in the ring is attached to 2 carbons already, 1 on either side, so it has 2 extra bonds left for hydrogens. So let's talk about some other types of skeleton drawings with other cyclic compounds. There are other ones besides the ones I just showed you. Again, each line represents a bond, and each bend and end represent a carbon. So we don't typically write the hydrogens bound to the carbon. There are a couple exceptions when we do. So here are 4 ringed molecules. And you'll notice most of the atoms in the ring are carbons. We have a couple that have, well, one that has a heteroatom in the ring, a nitrogen, and one that has a heteroatom sticking out, and then one that just has a carbon side chain sticking out. So if we were to draw this, we would drop the hydrogens except for the ones on heteroatoms. We always keep those. And everything else is turned into the line representing the bonds between them. So we would draw it like this. Now you notice the nitrogen is still drawn here, and we still show the hydrogen on it. And sometimes we would just write NH. We wouldn't even put the bond between those two. Just like we did with the OH here, we wouldn't show the bond between the oxygen and the hydrogen. It just takes up more space. These are much, much easier to draw, so the skeleton structures are strongly favored by organic chemists when they're drawing these molecules. So let's look at some of the rules for drawing a more complex organic molecule, the so-called skeleton or line structures. Remember, each bend and each end is a carbon. So here's a molecule here. This is actually Viagra. And every single bend you see that doesn't have a letter on it is assumed to be a carbon. I haven't put arrows next to every one of them. There's still plenty of others that are in bends. But there are also ends, you'll notice. Each of those ends is also a carbon, and you have to know how to count up how many hydrogens there are. So always keep in mind every carbon should have 4 bonds unless it has some charge on it, or unless something very peculiar is going on with the molecule, which happens on a rare occasion, but not in this course. So long chains of carbons will tend to look like zigzags. So for instance, in this particular molecule, we see this little zigzag starting to form with carbons, and if there were more carbons, we would just keep writing this zigzag, or we could write them sideways like this, and if you wanted to write branches, you could write a branch zigzagging off, etc. So there are lots of ways of drawing these, and many times when you have a molecule, there are multiple ways to show it, depending on how you move different atoms in different places. The rings tend to be drawn as very geometric shapes. Sometimes we draw them on the side, like as I showed you in the previous slide, showing more or less the true geometry, but most often they're drawn as if you're looking above the ring and they look flat. Again, we don't draw most hydrogens, though we do have a few exceptions. Just keep in mind the carbons have to have 4 bonds, so there have to be enough hydrogens to load them up. The exceptions are we always draw the heteroatoms. So you'll see in this the molecule at the top, we've drawn the nitrogen, the sulfur, the oxygen that are in each of those positions, as well as hydrogens that might be attached to them. In this case, there's only one on one of the ends in here. Occasionally, we will draw a hydrogen on a carbon, especially a carbon that only has a single hydrogen on it. You typically find that in groups that we call aldehydes, and we'll talk about those later. But I'll show you an example at the bottom of this slide. Sometimes we'll draw the methyl group out. We'll actually write out the CH3, especially if it's at the end here, so we might just write CH3 here instead, or even if it's at the end of a chain, just to show the chain ended, we can say CH3, but that's not necessary by any means. This is very common to see it if it's just one carbon, especially over here. You might see CH3 written there, but this is not necessary at all. So here's a wacky molecule that's very confusing. It has lots of atoms in it. You can see how it's very cluttered, and it's hard to envision what's actually going on. And maybe this is easier when you're first starting, but for a chemist that's used to looking at molecules, this is very annoying to look at. So we convert this to a skeletal structure. We eliminate most of the carbons. We eliminate almost all the hydrogens except the ones that are attached to heteroatoms. And maybe we'll keep the hydrogen that's attached to an aldehyde. This is an aldehyde group right here. It's a carbon with a double bond oxygen, and we'll learn about that in a later module. But you'll see there's only a single hydrogen on this carbon, so we'll typically draw that hydrogen in that case. But again, it's not absolutely necessary. So to redraw this, you'll see that this 6-membered ring over in this structure has been collapsed to a simple hexagon. We show the double bond by writing a double bond. We keep that. There's another double bond here, so we keep that as well. The heteroatoms are all kept. So we have double bonds to oxygens here that we keep. As I mentioned, we kept this hydrogen, but it's not necessary. It's kind of optional. We wrote out this CH3, but again, it's not optional. I could have just written NH, and you'll notice I put the H on the top of the N. That's fine. You can put it on the side. And I could have just drawn a line to represent what would have been the carbon here. And then the OH that was right here, you'll notice It's just simply OH. I don't write the bond between it. I don't write the bond between the N and the H here. I don't write it between the N and the H here. So you see these formulas can be quite simplified and making it easy. So at first they're going to be a little difficult to recognize, but after a while you'll strongly prefer to look at these, as almost every organic chemist does. So let's look at some skeleton structures of molecules you've heard of. Aspirin, naproxen, naproxen, also known as naproxen, also known as Aleve. This is the drug Aleve from Procter & Gamble, originally invented by a company called Syntex, which is no longer with us. Ibuprofen, which goes by a number of names, including Motrin. And then Lipitor, a drug used to treat high cholesterol. So we have these molecules. You'll see these skeleton shapes, and in some cases we have rings. You'll notice rings with alternating double bonds. These are very special kind of rings called aromatic rings. We'll talk about that in another module, but you'll notice some of these rings have quite a few double bonds in them, and that becomes important for drawing these molecules. But this is not cyclohexane. Cyclohexane would simply be the ring with no double bonds, all single bonds. This is a different kind of ring structure entirely. This is actually what's called the benzene ring, which you may have heard of. This ring right here is a benzene ring. Otherwise, the generic name for benzene type rings like this one and these here are called aromatic rings, but we'll talk about that at another time. So let's talk briefly about some of the basics of nomenclature for naming organic molecules. Organic molecules can be very complex, as you've already seen. So naming them can involve many, many rules. So we're going to keep to just the simplest rules for the simplest kinds of compounds, the alkanes and simple versions of alkanes. And in these cases, you always look for the longest chain, and you look for anything sticking out from the chain. We call those branches, we call them substituents, we call them side chains, we call them groups, and sometimes we have other things called functional groups, which actually are groups of groups of atoms in very specific patterns that give certain chemical function to the molecule. And we'll talk about those in another module as well. So IUPAC makes the rules for everybody to name everything in chemistry, including organic molecules. IUPAC is the International Union of Pure and Applied Chemistry, or chemists. They make the rules, and the rules can get incredibly complicated, but let's just look at the basics of the rules. So substituents, as I mentioned, is just a fancy name for side chains, things sticking out of the main chain. They may or may not be made of carbon. So here's one that we actually looked at already. This is the 2-methyl propane that we looked at earlier. So this was the one that, if I draw it in a skeletal form, it looks like that. We have a main chain with 3 carbons, and we have a single carbon sticking out. And I could redraw that like this instead, where we have 3 carbons in a row, and the middle carbon has another carbon on it with the appropriate number of hydrogens. So this would be our methyl group side chain or substituent, and this would be our 3-carbon main chain. So this would have a methyl side chain, or a methyl substituent, or a methyl group, or a methyl branch, and we would name the branch by taking whatever the length is. If this was 1 carbon, it was methane. If it was 2 carbons, it was ethane. If it was 3 carbons, it was propane. And since it's a branch, it now ends in YL instead of the original ANE ending. Non-carbon substituents are named differently, obviously. So not all substituents are carbons. Some substituents are halogens. These are the halo compounds. And you can have halo alkanes as well as halo other kinds of molecules. Halogens are the fluorine, chlorine, bromine, and iodine. And in that case, if you're naming them, instead of changing the fluorine, chlorine, bromine, and iodine ending to YL, we end it with O. So it becomes fluoro, chloro, bromo, and iodo when we're naming it. So the naming rules are the same thing. So for instance, if I had that same propane and I had an iodine on it, we would say that that was 2-iodo, and that's how you say that word, iodo propane, and you actually just run the words right into one another, propane. Whereas if I had 4 carbons here, and maybe I put a chlorine at the beginning, this would, since those carbons are numbered 1 through 4, and 4 is butane, and the chlorine is attached to the first carbon, we would call this 1-chlorobutane. And if you're going to be learning nomenclature, we have another module that's strictly about naming these compounds, so don't worry about getting it from just this module itself. This is just to introduce you to the concept. One other rule is when you have a number of substituents on the molecule on the main chain, we actually list them in alphabetical order. So we would write bromo before we would write chloro, before we'd write fluoro, and before we'd write iodo. So that would be first, etc. If the molecule had all 4, for instance, in it. All right. So there's another concept in organic molecules, and this is true for a lot of other molecules besides organic, but it's very common among organic molecules. We can generate what are called isomers. And isomers are molecules that have the same formula, but don't look the same. They have different structures. For example, C4H10, I already told you, was possibly butane. Butane is 4 carbons in a long chain. So it's CH3 to CH2 to CH2 to CH3. 4 carbons are all linked together in a long line. But you could also come up with a molecule that had 4 carbons and 10 hydrogens that looks different. And this is one we've already talked about, 2-methyl propane. If you count this, and you count up all the hydrogens, remember on the first one here, butane, remember there are 3 here, there are 2 here, there are 2 hydrogens here, and there are 3 hydrogens here, for a total of 10 hydrogens. But this one also has 10, there are 3 here, 3 here, 3 here, that's 9, and the middle one still has room for 1 more bond. So these are both C4H10 molecules, so you know that they have the same formula, but different structures and are therefore isomers. You have to have ways of naming them that are different so that we don't confuse them. It's not like ionic compounds where one name is related to one structure. You can have a lot of different structures for the same formula for an organic molecule. And in fact, the bigger the structure in terms of how many atoms, the more different possible isomers you can have. Just the formula for glucose, C6H12O6, can have dozens and dozens of different actual structures that have that same formula. So both of these formulas have 4 carbons and 10 hydrogens, and because they have different structures, we call them structural isomers. There are actually many types of isomers that you'll cover if you take an organic chemistry course. We won't cover them here. We'll only cover structural isomers, and you can just call them isomers for now. But if you can tell them, if they're different molecules that have the exact same formula in terms of the number of each atom, so you'll have to count all the atoms. You'll have to look at this and convince yourself that it really is C4H10 and that this really is C4H10. And once you're convinced of that, you'll know that they have the same total formula but different structures and are therefore isomers.